Welcome to Kino7.com. Please like, share and subscribe my video. Today we're going to look at the factors affecting the rate of reaction. In the previous video we have looked at how to calculate rate of reaction by using the amount of product made or by using the amount of reactant used up at a particular time. There are a few factors we're going to look at today, but first of all we're going to look at the collision theory. Now, look, particles always collide with each other, and only few collisions can actually make the chemical reaction to happen. Now, collision theory actually says the greater the number of successful collision, the faster will be the rate of reaction. So, for GCSE student, you need to learn the definition of collision theory. So, we're going to look at the first factor, which is temperature. Now, if you do know that temperature related to the heat energy, as you increase the temperature of a chemical reaction, you will see that the particles will start moving quickly. So, if I can give you an example of these particles who are going to react with each other by using the successful collision theory. Look at that. These particles are moving randomly, colliding with each other. They're colliding with the wall of the container, but they are not actually converted into the product. For example, you have air. Air is actually a mixture of gases, and you've got oxygen, you've got nitrogen in it. Nitrogen and oxygen particles are constantly colliding with each other, but they are not converting into nitrogen oxide. And the reason behind it that they do not have enough energy to actually collide with each other and make a new product. So if you increase the temperature by using heat, you will see that the particles will start moving quickly and they will hit each other very quickly as well. And the kinetic energy will be increased. So the heat is related to kinetic energy, and then they will start colliding with each other. And after this, they will have more successful collisions and will convert into product very quickly. So the whole thing is you have reactants into products, and we will look at the factors. Now, the second part is concentration. Before I move forward, I just want to actually make a point here how it looks like in the graph. For GCSE student, they might will give you a graph to interpret. Now look at this. If this is the volume of the gas produced, and this is the times taken in seconds. For example, if this is the volume you have produced at low temperature, so this is low temperature, and then if you increase the temperature, you will see that the amount of gas produced is higher at high temperature. Now the concentration, if you increase the concentration, you have more successful collisions. If you have more successful collisions, then you are going to have more products made, means higher rate of reaction. How? For example, if this is a container where you have 6 particles, I'm not gonna say that you have 6, but just an example, and then in the same container, if you actually increase the number of particles, you have low concentration and you have high concentration. Now, because you have increased the concentration, the particles actually is going to start colliding with each other more quickly, because the space between them is actually reduced and is actually been filled by the more particles. So they will have more collisions. More collision means they will have more successful collisions, and the rate of reaction will actually be higher by increasing the concentration. So in short, by increasing the temperature or concentration, the particle will have more successful collisions, and they will actually make more product. Hence, the rate of reaction will be increased. Now we're going to look at 3 more factors, and I'm just going to look at the pressure now. I'm going to remove that. So if you have pressure, the number of particles will remain the same. You use the same word again, that by increasing pressure, the space will be reduced between the particles, and you will get more successful collisions, or frequent, they will collide frequently, and rate of reaction will be rate of reaction increases if you do that. Now let's take an example. Let's take the diagram example where we can actually look at properly. So you have these particles there, and this is at low pressure, and then you have the same amount of particles again, but this time you have compressed it. So you can see this on this side, particles have more space to move, and here you have less space to move, and because of this the reaction will actually happen quickly. The space is smaller, and because particles are constantly moving, the liquid and gases, they will actually react quickly. Now they have more successful collisions, and the rate of reaction will increase. Now the last factor, the second last factor is actually catalyst. I'm going to actually explain surface area at the end, because there's a reason behind it. So the catalyst. So 2 people, let's just say Mr. A and Mr. B, they both are actually traveling the same distance, like 100 meter, and one of them is actually walking, and other one is actually using a cycle. Mr. B will reach on his destination of 100 meter quickly as compared to Mr. A. And the reason behind it, pretty obvious, he's using a cycle. So the cycle is actually helping Mr. B to actually move from this point to this point for 100 meters quickly. But at the end, there's nothing happened, so cycle is still the same. No chemically changed or mechanical change, nothing has happened to the cycle. Cycle is actually being used as a transportation purpose, and to decrease the distance, or to speed up the distance between 1 or 100 meter. Now, catalysts are the chemicals, just like cycle, which speed up the reaction. How? Number 1, they use by using alternative route and decrease successful collisions at low temperature. So these are two things to do, and I have already explained that in the one of the video. If this is the reactant, and let's just say it's an exothermic reaction, and this is the progress, and this is the energy, this is reactant, and this is product. If the reactants required the activation energy up to here, which is energy, let's just say is 100 kilojoules per mole, the catalyst will actually decrease that activation energy. So you can see that the MI will reduce to 70 kilojoule per mole. So the job of the catalyst to actually make the reaction happen at the low temperature, and it actually does it by using an alternative route. So it's just a job of like a cycle that will go from A to for A to B, or from 1 to 100 meter, and A to will unchain at the end. So chemicals which speeds up the chemical reaction, and also they are chemically unchanged. So at the end you will recover it. For example, let's just say, take an example. If you have hydrogen peroxide and you're converting into decomposing H2O2 and converting into water and oxygen, you can speed up this reaction by using potassium iodide. The potassium iodide actually works as a catalyst, and it will actually speed up the reaction. As a chemist, you should be actually reducing the cost to produce a chemical. So it can be a medicine, it can be a paint, or any other chemical in the industry. You have to use these sort of techniques to reduce the cost, and it will save some money as well. So that's why catalysts are really amazing while you do these processes. One of the processes, Haber process, N2H2 plus 2NH3, you produce ammonia, and you use actually iron. Iron is used as a catalyst, and that's why we have written that on the top of the arrow. Now the last bit is actually surface area. So if you want to actually pause it and you want to write it, you can do that. And the last one is surface area. And surface area also affect the rate of reaction. If you decrease the size, if you decrease the size of the particles, the rate of reaction increases. Now this is a common mistake people actually do when they look at a big piece of any substance, and they think, oh, it has more surface area as compared to the other. Now, for example, if you have a big block of marble chip, and the surface, if it's a cube, the surface which is available to react obviously is a cube, so 6 sides are available for the reaction to happen. So if you put this calcium, if this is calcium carbonate, and you are going to dissolve that into hydrochloric acid, hydrochloric acid molecules can only attack from 6 sides. So the particles on the top of the surface are only available for the chemical reaction. The particles which are actually inside are not going to react unless they are exposed to hydrochloric acid. So now what we're going to do, we're going to actually convert it, we're going to cut into pieces. So if I am going to cut that into small piece, the same cube, I'm going to cut that into small piece, you will see that this time I have got all the particles here. So I'm not going to draw all of them. So 6 sides, 6 sides, 6 sides, 6 sides, 6 sides, 6 sides. Before that, only 6 sides are available for the chemical reaction. After actually breaking them down into small pieces, and the surface area increases, because you can see that the air between the particles in between, they were not exposed before. After converting into small pieces, you can see that now more sides are available for the chemical reaction. And that is why I always insist, please do make sure that if you have a big marble chip, or you're doing a chemical reaction with the big marble chips, the rate of reaction will be slower. But if you're doing a chemical reaction with a powdered marble, it will be higher, because you have actually converted them into small pieces, and now they will react more quickly because more particles are available for the chemical reaction. And the equation is, if you have calcium carbonate which is going to react with HCl, it will produce calcium chloride and produce carbon dioxide and water. This is a reaction of the carbonates with the acid, and it's one of the famous ones which I've done already. Now, surface area to volume ratio is a different situation where we calculate that. Now I'm going to teach you how to do that. In mathematics, you do know that you can actually use area length time width. So for example, if this is a 6 centimeter a cube which has got 6 centimeter height, rest of the sides will be same as well. So do not get confused that they have only given you the height or length or width. If it's a cube, all the sides are same. So you will do 6 times 6 and you will get the area for that. Now calculate the surface area. Once you get the area of the one side, you are going to look at the 6 sides. So in total you have 6 sides in a cube, so 6 times the area, which you already got 36. So you would say 6 times 36, and because this is 6 sides, so you will get the answer here in centimeter cube. Once you get the surface area, which is SA, you can calculate the volume. And to calculate a volume of a cube or a rectangle, you see the height, width and length. For the cube is obviously, you can say 6 times 6 times 6, and that will be the answer for that. So that's 216, I believe, centimeter cube, not centimeter square. Okay, so that is the answer for the volume. And surface volume to surface area ratio, you can actually use that as a for the calculation. So this is how you calculate area and surface area and the volume in the question. You need to look at the video again if you do not understand properly. So in short, all these factors, temperature, concentration, obviously the pressure, they all increase the successful collisions, and the rate of reaction will be higher. Catalysts will also do the same job, but they actually lower the temperature, and the successful collision will happen at the low temperature. They use an alternative route, and that's why the rate of reaction will become higher. Catalyst always remains unchanged. That's why they are economically very feasible for us to use, because we can use them again for the next reaction. Then surface area, if you have increase the surface area by decreasing the size of the particle, like a cube converted into small cubes, or you have a grain and converted into a powder form, the rate of reaction will become higher because more particles will be exposed to the other reactant. Thank you very much.